This video covers Stat 454, Chapter 4, Section 7, Alternative Optimal Solutions to LPs or Multiple Solutions to LPs. Take a look at this LP that I am highlighting on this sheet. It's an LP that comes out of one of the sections in your textbook. The way we decide the value of the basic variables is by identifying all of the columns where a variable is by itself in the column and assigning the basic variable that value. That makes all of the other variables non-basic variables, and their values are 0. So for example, z is all by itself in this column. Its right-hand side is 280, which creates a basic variable value of z equals 280. You can repeat this process on x1 equals 2, on x3 equals 8, etc., etc. This makes the variables like x2, s2, s3, and there's a typo right here. There should be a 1 here. This makes x2, s2, and s3 non-basic variables whose values are set to 0. Now, this tableau is an optimal tableau because all of the coefficients in row 0 are non-negative. No matter what value of a variable I choose as the entering variable, I won't be able to increase the value of the LP. So for example, right here, if I entered S2, I would actually be decreasing the value of the LP by 10 for every piece of S2 that enters into the basis. That's what these positive coefficients mean. But take a look at this 0 coefficient. This is a column that indicates a non-basic variable. In other words, x2 is valued at 0 here. But this coefficient of 0 says, if I increase x2, z will increase by 0. In other words, increasing x2 in this table does not change the value of the LP, the optimal value. So I can perform the usual elementary row operations on this column with a 0 coefficient on a non-basic variable and not change the value of the LP. Let's perform the usual row operations, the ratios. -12 here, I'll ignore it. -4 here, I'll ignore it. 2 over 1.25, I'm not sure what number that is offhand, but it's positive. And then 1 over 1 is 1. This is definitely the smallest value. So I'll perform elementary row operations to eliminate. Let's see, I did them previously. It looks like I need to eliminate them in row 3. So this value right here will be the winner of the ratio test. So using elementary row operations to cancel this value, and this value, here they are as they would appear in your calculator, creates a tableau that looks like this. Let's perform the same kind of reading. Z is by itself, it's a basic variable. Its value is 280. So Z has not changed its value. Non-basic variable. X1 was previously a basic variable, now it's not. X2 is a basic variable. X3 is a basic variable. S1 is a basic variable. You can read all of their values off on the side here. And then finally, S4 is a basic variable right here. So this collection in this right-hand side, these 4 basic variables are a different optimal solution compared to the 4 basic variables of last time. Recall from our visualizations all the way back in Chapter 3 that the way we saw an optimal solution, an alternative optimal solution arising was when the isoclines were parallel to one of the constraints. And as the line was increasing, we saw that it lay on the constraint itself. What does that mean for our purposes? That not only are the corners alternative solutions, but so too are all points on the line segment between them. So all of the points on the line segment between these two corner points are also alternative solutions. So I'm going to tell you how to actually create that line segment. So what I'm going to do is label these 2 points. I'm going to label A1, the alternative solution number 1, to be this column vector, 2, 0, 8, 24, 0, 0, and 5. This is the column vector associated to x1, x2, x3, s1, s2, s3, and s4. I'm going to write a second column vector A2 associated to the solutions that arose from the second tableau. Those look like 0, 1.6, 11.2, 27.2, 0, 0, and 3.4. Again, the first number is associated to x1, the second one is associated to x2, etc., etc. The way you can create a line segment containing all of the points in between these two is this way. So for 0 less than or equal to t less than or equal to 1, create the line segment of the form. I'll call it A for all alternative forms. T A1 plus 1 minus T A2. This is the formula that will let you create all of the alternative optimal solutions. Let me give you a little bit of interpretation on what this expression looks like. When t equals 0, you have that A equals A2. Plug it in t equals 0 into that expression to see what you get. And then when t equals 1, you get that A equals A1. In other words, at the beginning, the solution looks like A2. At the end, the solution looks like A1, and different values of t move between A1 all the way to A2 and vice versa. So you can actually do a little bit of arithmetic to combine these two expressions. Follow them down here. This gives a form of A when I combine like terms to look like 2t, 1.61 minus t, 11.21 minus t plus 8t, 27.2, 1 minus t plus 24t, 0, 0, and then 3.41 minus t plus 5t. This is the expression that arises when you combine the two parts of A piece by piece. Multiply everything in here by t, multiply everything in here by 1 minus t. So You will have a homework problem based on this. This is the form of all of the alternative optimal solutions. This is the form of everything that lives on this line segment. So no matter what value of t you pick, you should still maintain the optimal value. So for your homework, pick t equals to 0.5 on this expression. Evaluate a of 0.5 and plug that value into the original LP in chapter 4.7. Your textbook describes where to find that original LP and the modifications they do to it in the second paragraph of 4.7 on page 153 of the textbook. That completes all content associated to alternative optimal solutions.